All right, ladies and gentlemen, today's recording has started. So, the past couple of days we have been discussing this idea of mechanics, the study of motion. And we said studying motion first starts with describing motion. And in order to describe motion, we need to know four things, right? What are the four things that we need to know? Joe, what's one? Where is the object? Drew, what's two? What is it doing now? Edie, what's three? What will it be doing next? And Nora, what's four? When do all these things happen, right? So, first thing we talked about was position. We said, position, separation between an object and some reference points. We can describe where something is as long as we describe it in relation to other things, right? And that's our reference point. And then we talked about that really getting into describing where something is not only requires a reference point, but also a directional system. So we can talk about things being here versus there, right? We talked about the idea that we're going to go one dimension, right? Only a straight line, all that fun stuff, okay? And we then talked about when something starts moving, how its position changes. And yesterday we talked about displacement and distance. So, how are they different from each other? How are displacement and distance traveled different? All right, go ahead. Distance is total amount of the trip, regardless of what? Regardless of the direction that we go, right? And that makes distance traveled what kind of a quantity? Somebody want to help her? The other one, scalar, okay? Distance is a scalar because it doesn't depend on direction. We just keep adding up how far we go, right? But displacement, right? What does displacement depend on? When we're figuring out the displacement of something, what do we need to know? Eventually, yes, but what do we need to know to determine the displacement? Where we start and where we finish, right? The final position and the initial position. And then we want to talk about how far from the starting point do we end up, but also we have to describe what? Which direction we've gone, right? So we talked about the difference here of these two lizard motions, right? One going one way, one going the other way. How do we distinguish this way from that way? Positive, negative, right? Okay, good there? So that handles where the object is and what if the object moves where it is, okay? Yesterday, we started talking about what is the object doing now. And at the end of class, we introduced the concept of speed, right? What does speed tell us? Or what is speed a relationship between? Distance and time, right? So speed is equal to d over t, or the rate at which distance is traveled, right? What does speed not tell us? Which direction it goes, right? So going back to these two pictures of the lizard, right? Did we get any numbers on this picture yesterday or no? Okay. So let's back it up a little bit then, and let's talk about velocity, right? We did introduce velocity yesterday, right? Right at the very end, right? Did we get the formula? Yeah. Okay. So velocity, the rate of displacement. So we talked yesterday, if we describe anything as a rate, what does that mean? You use time. You compare it over time, right? Whatever happens over time, all right? So here, if velocity is the rate of displacement, it's displacement over time, right? Are we good with the delta x notation, the triangle x? Is that good from the other day? Do we remember that or no? Right? The delta, the triangle, stands for what? Change, right? And so if we talk about the change in x, remember we kind of talked about this idea that as this lizard is moving sideways, either this way or that way, we could imagine it moving along the x-axis of a graph. Yes? Does that sound familiar? Yeah? Okay. But because it's only moving in one dimension, it can only move on the x-axis. So a lot of times we will represent displacement with delta x, the change in where it is on the x-axis. Is that good? Does that sound good? All right. We still measure velocity in meters per second, but then, and this is I think where we left off yesterday, right? With the picture of these two lizards here? Okay. All right. So on the front side of your outline, we calculated the displacement of this lizard for these two trips, yes? All right. What did we say this first displacement was? I can't remember what you guys decided the first displacement was. 64 centimeters, okay? So 64, no, 60 centimeters, right? Is that enough to give us the displacement? No. Positive 60 centimeters, right? Because we got to give direction, okay? And then this one, right? This one was 64. This one was 64, okay? But it's not 64, it's actually what? Negative 64 centimeters. Okay, good with those? Those are just straight from the front side, okay? But if we want to calculate the velocity, we have to compare the displacement to what? Or look at the displacement over what? Over time. So we've got these two stopwatches here, right? The first stopwatch in this trip starts at 0, and it ends at 4, okay? So the time that this displacement takes is what? 4 seconds, okay? Now, if we want to be consistent with stuff we talked about in the last unit, right? 1, 2, 3, 4, 5. That makes the ones place our certain digit, yes? So our measurement has to go where? To the next place, right? To the 10th place. So this really isn't 4 seconds, it's actually what? 4.0 seconds. Okay? And I think we talked yesterday right at the end of class. Here, 20, 30, 40, 50, the tens place is our known digit, so our measurements have to go to the next place, right? So this, the ones place, right? Yeah. So this would actually be 60 dots, or 60 point centimeters, right? Not 60.0, but just 60 because we have to make that 0 significant, okay? Good there? All right. So we just learned that velocity is displacement over time. The displacement is positive 60 centimeters. The time is 4.0 seconds. So that means that the velocity of this lizard is equal to what? Does anybody do this? Can anybody do this without putting it through their calculator? Okay. So 15 centimeters per second. Or is it? Not 15.0. Okay, 15. The centimeters per second is something important. I just forgot to do that. But more importantly here, right? Which way is this 15 centimeters per second? In the positive direction, right? So positive 15 centimeters per second. Okay? Good there? All right. Coming down to the bottom trip, the displacement is negative 64 centimeters. This stopwatch starts at 6 and ends at 9. So what time does it take? 3 seconds, right? And that'll be 3.0 seconds, just for what we talked about before, right? Okay. So then, the velocity, right, turns out to be what? That's what your calculator tells you, right? How many significant digits? There can only be 2, right? So that means the 2 would be significant. The 1 would be significant. We look at the next number, it's a 3. Do we have to round anything? Nope. So we would just round this answer here to 21 centimeters per second, right? But is it 21 centimeters per second? Okay. If the displacement was negative, the velocity is negative as well. Okay? Good there? What does that tell you about velocity? What do we call those things that can go both ways? Well, that is the direction. What do we call quantities that depend on which direction they go? Vector quantities, right? So, velocity is a vector quantity. It has magnitude. In this case, the magnitude is how fast something is moving. But it also has direction. And like we talked about, in one dimension, on a straight line, what are the only two directions something can go? Left or right, or up or down, or front or back, right? But we distinguish that by doing what? Positive or negatives, right? All right, how's that? Okay. Question before we move on to the next part. True or false? Okay, I won't have you talk at this point. I'll just have you mentally engage with this problem. Okay, mentally engage. Think in your head. Okay? Think. Don't yell. Think. Don't yell. True or false? Speed is the magnitude of velocity. True or false? Speed is the magnitude of velocity. All right. Show of hands. Speed is the magnitude of velocity. True. False. Really don't know. All right. So, we said magnitude is a fancy word for what? How much or how big, right? Here, velocity being a vector, it has magnitude. The magnitude of velocity is how fast something is moving. What do we call how fast something is moving? Speed. What does speed not tell us that velocity does? Right? So here, right? What's the speed of the lizard in the red case? 15 centimeters per second. What's the speed of the lizard in the blue case? 21 centimeters per second. Doesn't matter which way we're going, just how fast it's going, right? Question. Well, this should be an easy question to answer now, right? Because we just did this, right? Which one's faster, positive 15 or negative 21? Negative 21 is faster, right? Even though it's a negative number, the negative just tells us direction. Okay? Good? All right. Finally, right? Third question. What will the object be doing in the future? Okay? So, warning. Warning. The next term we're going to introduce is a term that you're familiar with. You've heard it before. You know what it means. But I'm going to tell you right now, what you think it means is not its full definition. Okay? It's one example of what it means, but not the whole story. Okay? Exactly. It's much like the Matrix. So. All right. So, what will the object be doing in the future? Okay? Acceleration is what tells us that. By definition, the rate at which velocity changes. The rate at which velocity changes. Let me do this, hold on. I'm going to slow you guys down here. So, just to review some of the things we've talked about over the past couple of days and make sure that we see how it applies here, right? As we've discussed, rate implies that we're measuring something how? Or against what? Time, right? If we talk about velocity changing, right, what notation could we use for that? What symbol do we use to represent change? Delta. So if the velocity is changing, it's what? Delta V, right? This is the rate at which velocity changes. Does that make sense? So acceleration is equal to delta V over T. Delta V over T. Okay? Does that make sense? Okay. Oh, not what I wanted to do. How much is the motion of that object changing? How much is the motion of that object changing? That's the important part. It doesn't tell what's happening now. It tells what's going to be happening in the future. Right? Acceleration tells us what will happen. Not what's happening now, but what will happen. Good there? And then finally, right? Not what I wanted. Okay. Acceleration is the change in velocity divided by the total time. And that's our formula for calculating acceleration. Okay. Good there? Let's talk about units. What do we measure velocity in? Meters per second. What do we measure time in? Seconds. Okay? We have a complex fraction here. But that complex fraction, I think, is actually a better description of what acceleration tells you. Meters per second. How much does the velocity change every second? Does that make sense? Okay. A lot of times you will see this fraction simplified to look like this, meters over seconds squared, which mathematically is an equivalent fraction. However, it can be a little misleading. First, what is seconds squared, right? You can't really measure seconds squared, right? Two, if you measure an object that travels, let's say, 10 meters, and let's say it takes 2.7 seconds to go those 10 meters, if you take 10 meters and divide it by 2.7 squared, you don't get the acceleration. Okay? This is not a formula. This is a simplified fraction of this one. This one is a description as far as what acceleration tells you. Okay? Meters per second. How much does the velocity change every second? Okay? Good there? All right. Here's where it can get a little tricky. Like I said, you guys know the term acceleration. You know what it means. You could give me an example of acceleration. However, that example is not everything that could be considered acceleration. What has to happen in order for acceleration to occur? Change in velocity, right? So, the first thing we think of when we think of change in velocity most of the time is what? Well, what change in speed specifically? If I say something is accelerating, most people think of what? Going faster, right? Is going faster a change in velocity? Yeah. Sure it is, right? So that is one example of acceleration, when things speed up, all right? Down at the bottom, letter E, I already told you before, three things that we consider acceleration. is speeding up. That's what most people think of as acceleration. That's let me see, but yes. So if speeding up is a change in velocity, what else is a change in velocity? Slowing down is also a change in velocity, right? Here's a situation that most of you are probably pretty familiar with because it happens a lot around here. Like when you're going home and boulders just kind of like start rolling after you. All the time. I know, all the time. Right? You walk by the rec center and things just go down that big hill. You're like, oh man, here it goes again. So, right? Exactly, exactly. But eventually, what happens to that boulder? Slows down, right? Okay, and eventually it stops. Okay, obviously, or else you wouldn't be here, right? But that's a change in velocity. Okay, and finally, right, Jason, the third one is going to be what? Changing directions. Remember, velocity is a vector. It tells us how fast, but it also tells us which way. If you go around in a circle, like on a carousel, it even says carousel right on there. Because apparently when I screen captured it, I was on the picture. So, just in case you didn't notice, right? Just in case you couldn't tell, right? So, right? When you're on a carousel, in the middle part of the carousel ride, you're not speeding up or slowing down, but you are still accelerating. Because you're constantly doing what? You're constantly changing direction. 1 second you're going this way, the next second you're going this way, the next second you're going this way, right? That's acceleration. Even though you might not be speeding up or slowing down, it's still acceleration. Okay? Good there? If acceleration can mean these different things, especially these two, speeding up or slowing down, how do you think we have to distinguish between speeding up acceleration and slowing down acceleration? Positive and negative, right? Now, I'm going to give you a general statement, and then I'm going to make a statement after that, and then hopefully you guys will respond the correct way, okay? Acceleration's a vector, okay? It has a magnitude, but then it also has direction, okay? The magnitude of acceleration tells us how much is the velocity actually changing. How much does it change by? But then the direction tells you, well, what happens to that velocity? Does it get bigger by this amount, or does it get smaller by this amount? This statement here that I just highlighted up on the board is a general statement meant to introduce you to this idea of positive and negative acceleration, but it is not 100% correct. Okay? Your sophisticated brains can handle this discussion, at least at this point. Okay? This won't be like a question on the quiz tonight, but just let's talk about this statement. Okay? I will show you that positive acceleration doesn't always mean speeding up, and negative acceleration doesn't always mean slowing down. Okay? And it comes back to this. All right. That's how we calculate the acceleration, delta v over t. We said delta means what? Change. In order to figure out the change in anything, what do you need to know? Initial and final. How did it start? How did it end? Right? And so we can write this equation to look like this. Okay? Good. Does that make sense how I went from that to that? Okay. Final velocity minus initial velocity over time. Okay. So let's talk about the first example, something speeding up. Here is, oh yeah, we got it. All right. So here's a car in my physics world, okay? So, what? You wish it was your car? Is that what you said? It's kind of like a cross between a flying saucer and a Volkswagen Bug. That's kind of what it's a cross between. It's vintage. So. It's a low mileage car. So, but it's vintage. It's vintage though. Okay. So here is my reference point. I marked it as 0. By the way, if you want to go with this, you can. The back side of this outline is completely blank, so if you want a little bit more room to draw, you can. Like I said, this discussion is not going to be like on your quiz tonight. Okay, this is a little bit of a higher level kind of thing, but let's go with it. Okay. All right. So I drew myself a car, even though the wheels aren't on the ground, but that's okay. The wheels go into the ground. But I gave myself a reference point. I marked it as 0. And I said that positive is towards the right and negative is towards the left. Okay? If I add some whoosh lines onto this car, right? That's what I call my lines to show movement, the whoosh lines. Because that's what noise this car would make. Whoosh. Right? So, how would we describe this car's velocity? Maybe not yet. You don't know that. But there's one thing you know. What? Well, whoosh lines doesn't mean it's going faster. It just means that it's moving. Right? It's positive velocity. And we know that because, Matt, which way is it going? In the positive direction. Okay? So, positive velocity. Okay? Drew? I'm not going to draw a completely new car, but over here, the whoosh lines now look like this, okay? So what has happened from this point to this point? What? No, it's going that way. All right, hold on. That clearly did not work. Oh. No, it's the same car. Okay. Okay, it is accelerating. If we were watching it, how would we describe it? It's sped up, right? It's moving faster. In this case here, okay, no numbers, right? No numbers. How would this car's final velocity compare to its initial velocity? It's greater. So if the final velocity is greater than the initial velocity, when we subtract them, we'll end up with a positive number on the top. So in this case, we have an example of, with the black whoosh lines, we have an example of positive velocity and positive acceleration. And that results in what happening to that car? It goes faster. It increases in speed. Okay? Good there? Okay with that? Yeah. Okay. Okay. All right. So, Okay? Physically, if we were looking at this blue car, how would we describe it? If we were watching it, what would we see happening to it? Well, yes, it increases in size, yes. It is negatively moving, so it has a negative what? It has a negative velocity, okay, because it's moving in the negative direction. Okay? Physically, if we watch this car moving in the negative direction with its negative velocity, what happens to its negative velocity? It speeds up, right? It's going faster, but it's going faster in the negative direction. Okay? This is how we calculate acceleration, right? Negative and negative. This negative is bigger than this negative, right? If we want to put some numbers on it, let's do this. Let's say this is negative 5 meters per second, and this is negative 2 meters per second. Okay? If we plug them into this equation, right, negative 5 is the final velocity, negative 2 is the initial velocity. But we have to subtract negative 2. So you're really adding, right? Negative 5 minus a negative 2 is not 3, it's what? Negative 3. So when we do the acceleration, we come out with what kind of acceleration? A negative acceleration. But what happened to this car? It went faster, right? So here's the gist. Okay? This positive acceleration is not always speeding up. It can be as long as the car is moving in which direction? Well, in the positive direction. Negative acceleration is not always slowing down. Negative acceleration is slowing down if the car is moving which way? So negative acceleration is slowing down if the car if it has a positive velocity. Right? So if they're different, the car slows down. If they're the same, the car speeds up. It doesn't matter if they're both positive or if they're both negative. Sorry, when I say them, I'm talking about velocity and acceleration. If they're the same, we speed up. If they're different, we slow down. Okay? Again, that won't be a question on your quiz tonight, but it's something we can think about as we move along here. Okay? Yes, Jason? We will get to that eventually. Next week, after we talk about graphs, we'll get into like the mathematical examination of this idea that we just talked about. Okay? All right. I will give you a quiz. Take it home. Bring it back tomorrow. Complete it, please. Thank you. Without looking stuff up on the internet and cheating.
You will never
just got that on the recording. All right, everybody? Yeah.